This video is an introduction to uniform circular motion. When we talk about uniform circular motion, we're specifically talking about something that's moving in a circle at a constant speed. This is not something that's speeding up as it goes around the circle. We're looking specifically at the speed of the object staying constant as it moves around a circle. A new quantity that's important to talk about as we talk about uniform circular motion is the quantity called the period. The period is the time that it takes for the object to go once around the circle. And that term period is used for other things. Anything that repeats itself over time. The period is the time that it takes for one full cycle of its motion. The period is going to be how much time, measured in seconds, that it takes for one full trip around the circle. To find the speed of the object, we've already talked at the beginning of the year that speed is distance divided by time. And so for something that's going around a circle, the distance that it travels is the circumference of the circle, 2 pi r, and the time that it takes to go around the circle once is the period. So the speed is the distance, 2 pi r, divided by the time, the period. Again, the period is how many seconds for one revolution. It's seconds per revolution. And so to find the speed, we take the distance traveled, that length around the circle, that circumference of the circle, and we divide by the period. If it's moving at a constant speed, which is uniform circular motion, the velocity vector has a constant magnitude. The speed is the magnitude of the velocity, but the velocity is constantly changing direction. In this picture, at one point, the velocity vector is to the left. At another point, the velocity vector is down to the right. At another point, the velocity vector is up to the right. And so the direction of the velocity vector is changing. So it would not be correct to say that this has a constant velocity, but this object has a constant speed. The magnitude of the velocity is staying constant. The definition of acceleration is change in velocity divided by time. And the direction of the acceleration vector is the same as the direction of the change in velocity. Change in velocity means the later velocity minus the earlier velocity. And so in this diagram, if we look at the velocities, and we're looking at the bottom part of the circle, the earlier velocity is this velocity that's down to the right. The later velocity is this velocity that's up to the right. If I go to subtract those two velocity vectors, to subtract vectors, I use the tail to tip method. I do the later velocity plus the opposite, so that's what it means to subtract, plus the opposite of the earlier velocity. And so the direction of the change in velocity at this bottom part of the circle is straight up. You could do this for any two pairs of these velocities, and you would see that the acceleration would be in towards the center of the circle. If something is moving around a circular path at a constant speed, the acceleration vector is in towards the center of the circle. The name that we give to that acceleration is the centripetal acceleration. Centripetal means center seeking, or towards the center. We sometimes also refer to that as the radial acceleration. It's along the radius of the circle. So if something is moving in a circle at a constant speed, the acceleration vector must be in towards the center of the circle. That acceleration has nothing to do with the speed changing. It has to do with the fact that the direction of the velocity is changing. The instantaneous velocity is always tangent to the circle. The direction it's moving at any one point is tangent to the path that it's moving along. And in uniform circular motion, the acceleration vector is in towards the center of the circle, along the radius. And in geometry, you learn that a tangent line to a circle is perpendicular to the radius of the circle. So here, the instantaneous velocity vector will always be perpendicular to the acceleration if we're talking about uniform circular motion. The key thing that's happening here is this acceleration is only changing the direction of the velocity. It's not changing the speed of the object. If you have non-uniform circular motion, where the speed is also changing, you would still have a component of the acceleration that's in towards the center of the circle, but there would also be a component of the acceleration that would be tangent to the circle, either in the direction of the velocity or against the direction of the velocity, and it would be that component that would be changing the speed. The perpendicular component, that centripetal component, or the radial component, is responsible for changing the direction of the velocity. The tangential component, the component of the acceleration that would be tangent to the circle, would be responsible for changing the speed. Because we're talking about uniform circular motion, where the speed is staying constant, we do not have a tangential component to the acceleration. We only have this component in towards the center of the circle, along the radius. Now, this slide, really the only thing that's going to be important from this slide is this equation that's circled down here, that the acceleration is the speed squared divided by the radius. The acceleration is v squared over r. But I want to just take a second and talk about the proof of this. It's not going to be important to understand, but I want to show people that this is not a new definition of acceleration. This is still just doing change in velocity divided by change in time. And so in this picture, we show one velocity vector. It has an x component and a y component. We have this later velocity vector. It has an x component and a y component. Just to make things easier, we picked some symmetry. So the first point is some angle to the left of the y-axis. The other point is the same angle to the right of the positive y-axis. The x components of the velocity are the same at those 2 points, so there's no change in velocity in the x direction. The change in velocity in the y direction, it would be this later y velocity minus this earlier y velocity. It gives us a change in velocity that's downward. Again, the key thing with this is at that point that's halfway in between, the direction of the acceleration is downward. It's in towards the center of the circle. Speed is distance divided by time. The distance that it travels just in this little small piece is the arc length. Arc length is r times theta, where theta is in radians. And so the time is the arc length divided by the speed. The magnitude of the acceleration would be the change in velocity, which we found up here. It's 2v sine theta divided by the time, which was 2r theta divided by v. And so if we simplify that a little bit, we get that the average acceleration is v squared sine theta divided by r theta. And what we're interested in is the acceleration right at point P. We want to let these two velocity vectors get closer and closer and closer together. We want to look at the limit as the time interval shrinks to 0, because that's the definition of instantaneous acceleration. It's delta v over delta t. It's the limit as delta t goes to 0. And so as we let those two velocity vectors get closer and closer together, that's equivalent to letting these two angles get smaller and smaller and smaller. And so if we look at what happens to sine theta over theta as theta approaches 0, this shows us in a table. In calculus, you learn about limits. But looking at this, if we have theta in radians, the smaller I make theta, that ratio of sine theta over theta gets closer and closer and closer to 1. The limit of sine theta over theta as theta approaches 0 is 1. And so the instantaneous acceleration is the speed squared divided by the radius. Again, you're not going to be asked to do a proof of this. The point of showing you this is so that you do not think that this is a new equation for acceleration, that we're doing something different to get acceleration. It comes from the same definition of acceleration that we did at the very beginning of the year. Acceleration is change in velocity divided by time, but because the speed is staying constant, but we're trying to take into account the direction changing, the acceleration is the speed squared divided by the radius. To understand this equation conceptually, the faster something is moving, in a certain amount of time, it's going to move farther along the circle, which means that the direction of its velocity changed more. And so the faster it's going, the faster the direction of its velocity is changing, so the larger the acceleration should be. If the radius is smaller, even though you might have the same speed, going the same distance on a smaller circle, it's going to get farther around the circle. And so for a smaller radius, the acceleration is going to be bigger. For a smaller radius, the direction of the velocity changes more per second, so you have a larger acceleration. So that's the more important thing, is understanding conceptually. The faster you're going, the more the direction changes per second, so that increases the acceleration. The smaller the radius is, the more your direction changes per second. So that also increases the acceleration. Because acceleration is meters per second squared, v squared is meters squared per second squared divided by meters. That gives us meters per second squared. And so that's a way to double check that you didn't forget to square the velocity. Make sure that your units work out correctly. And so if something is moving in a circle, the direction of its velocity is changing. If the direction of the velocity is changing, it is accelerating. Newton's second law told us if the object is accelerating, there must be a net force. There must be an unbalanced force acting on the object. Newton's second law tells us that the net force equals the mass times the acceleration. For uniform circular motion, the acceleration is v squared over r. And so when we go to calculate the net force from F equals ma, we substitute in the acceleration is v squared over r. The direction of the net force and the direction of the acceleration must always be in the same direction. It's the net force that causes the acceleration. And so the direction of the net force is always in towards the center of the circle for something in uniform circular motion. Net force is just the name for all of the forces added together. Net force is not a new force by itself. And so the net force is the sum of the individual forces. You might have tension in a string. You might have the force of gravity. You might have friction. You might have several of these forces acting on the object, and it would be the sum of those forces. So just like in other problems where the net force is the individual forces added together, we have to look at the situation and look at what individual forces are acting, and then we set those equal to mass times acceleration. Again, this net force towards the center of the circle we sometimes refer to as the centripetal force. Centripetal means towards the center, and so the centripetal force is the net force towards the center of the circle. It's not an extra force that's acting. That centripetal force is tension or gravity or friction or some other combination of forces. You add your forces together, and that net force towards the center of the circle we sometimes refer to as the centripetal force. So now I'd like to look at a couple of basic examples. In a separate video, we'll look at a couple of situations where there's more than one force acting. In this first example, I have a ball that's tied to a string. The length of the string is 0.392 meters, and it makes 3.2 revolutions every second. The first thing that we're asked is to find the period of this object. 3.2 revolutions per second is a quantity called the frequency. Revolutions per second is how many revolutions it's making in 1 second. The period is seconds per revolution, how many seconds it takes for 1 revolution. The period is the reciprocal of the frequency. If we know that it makes 3.2 revolutions in 1 second, then the time that it takes to go around once would be 1 over 3.2. The period, the time that it takes to go around once, is 1 second divided by 3.2 revolutions, or 0.3125 seconds to make 1 revolution. If it's going around over 3 times in a second, it takes less than a second. It takes about a third of a second to go around once. And so the next thing we want to find is the speed of the object. This is the way that we measure the speed for something that's going around in a circle. We will measure the period of the object. We can use a stopwatch to measure how much time it takes to go around once. And then if we can measure the radius of the circle, we can easily calculate the speed. The speed is 2 pi r over the period. It's the distance traveled, the circumference of the circle, 2 pi r, divided by the period. The radius was that length of the string, 0.392 meters. And so this was 2 pi times 0.392 meters divided by the period, 0.3125 seconds. And so the speed of the object is 7.882 meters per second. Again, we just find the distance that's traveled from the circumference of the circle. We find the time that it takes to go around the circle once, that's the period, and we just do that distance divided by the time to get the speed, because the speed is constant. This second problem is similar, except it's going to go an extra step. So we have a model airplane with a mass of 0.6 kilograms, and it's attached to a horizontal string, and it's being swung around in a horizontal circle of radius 5.9 meters. And it makes 2 revolutions every 6 seconds. The weight of the airplane, the force of gravity on the airplane, is going to be balanced by the upward lift force, and so the only unbalanced force that's acting on this airplane is the tension in the string in towards the center. So the first thing that we want to calculate is the speed of the airplane. To find the speed, we need the period. The period is how many seconds it takes to make 1 revolution. If it makes 2 revolutions in 6 seconds, that means that it took 3 seconds to make 1 revolution. The period was 6 seconds divided by 2 revolutions, or 3 seconds per revolution, 3 seconds for 1 revolution. The speed is 2 pi r over the period, and so that's 2 pi times the radius, 5.9 meters, divided by the period of 3 seconds. And so the speed of this airplane is 12.351 meters per second. Next, we want to calculate the tension in the string. The only unbalanced force that's acting on the airplane is the tension in the string in towards the center of the circle. So the net force that's acting on the airplane is that tension in the string. And net force equals mass times acceleration. Because it's moving in a circle, the acceleration is v squared over r. And so the tension would equal the mass times the acceleration. It's 0.6 kilograms times the acceleration, v squared over r. So it's the speed, 12.351 squared, divided by the radius of 5.9 meters. That gives us a tension in the string of 15.53 newtons. Again, in this example, there was only 1 unbalanced force. In a separate video, we're going to look at situations where things are moving in a vertical circle and you have more than 1 force acting. And so your net force needs to take into account all of those forces. Here, when there's just a single unbalanced force acting, that unbalanced force is the net force. And so you can calculate that force from Newton's second law. The net force is mass times acceleration.